Log on, tune in, find out. Another good idea from Cambridge.
From the University of Bristol, and he will talk to us about generalized dynamical system, and you see a picture of the latest advances in high technology.
You've just taken my joke away from me. Is this working?
This is for recording purposes.
I see. Right. So, of course, as you know, I'm not a computability theorist, but I thought for this series of talks I have to do something Turing-ish, and I've got here a rather hubristically dangerous title, given what a large field dynamical systems is, but I would like to give you something that is perhaps at least something you can think about for amusement on wet Sunday afternoons. Yes, this is a Faraday disk. It's not the first computer of Isaac Newton or anything. Right. What we'd like to do is just think about the idea of a dynamical system, but where we would normally think of a dynamical system, you perhaps have a continuous function on some n-dimensional torus, and you would look at iterates of points as the function is applied to the finite natural numbers. Let's try thinking about what happens if you do this transfinitely, just for our own amusement here. So we're going to look at variants of such systems, and we can think of perhaps these as being modeled by transfinite machine models, Turing register machine or Bloom-Shub-Smale machines. So an example. So just take any function on intervals of n to n, and think of this as being just an n-dimensional lattice torus, where we're going to identify infinity here with omega. So the natural numbers stretch out to infinity. Infinity comes back to 0. And what follows on the next 3 lines are just how one could set up some definitions for iterating this function. So at the 0th point, we start out with some input, R1 up to Rn, so this is just a point on this torus. At successive stages, we apply the function to this point, and this gives us the coordinates of the next point here. And of course, we have to decide what to do at limit stages. And what we're going to do is take lim-infs of the coordinate-wise of those values. Right? So for the ordinary, if the coordinate stays bounded below omega, of course the lim-inf just has an ordinary meaning. But of course the function on a particular coordinate may go up towards infinity, in which case it's going to come back to us as 0. And that's all what this lim-inf star means here. So we just define the lim-inf star of the iterates of a particular coordinate here as alpha goes towards, well, omega or some other limit ordinal, lambda here, to be the ordinary lim-inf if this value is less than omega. And otherwise, if the thing has crept up to omega, we just reset it to be 0. Okay? Any queries here? Okay, I think it's straightforward. Okay, so we envisage this torus, right, like this with these lattice points on it. We've got a function. We haven't said anything about the function, really. But you then say, well, there are going to be some points on this torus that perhaps get sent eventually as this thing iterates through to the origin. Right, so what are these origin sets, right, if you like? So 0 set, I called it here. Look at the points in n to the n. So after some alpha many stages, however many this is, the point gets sent to the origin. So just call this the 0 set. Okay, so perhaps a more amusing example. Just look at triangles. All right, so take a triple of points on the torus here. Reapply the function all the time with this funny funny liminf at limit stages. Okay, a general triple of points, it's a proper triangle, and you could ask, well, which triangles collapse to a point? Or which triangles become collinear? Or which triangles stay forever triangles, as we reiterate in this way? Right. So clearly there's a set of points, a set of triangles, right, on the torus here that will perhaps stay forever triangles. Maybe it's empty, maybe not. Right? So obviously it's a function of f. How do we identify these sets? Right? How long do we have to wait until we know of a particular triangle whether it's going to be collapsed or not? Right? We just set the machine running and we just see how long it takes. And we'd like to know how many stages we have to go through to find out whether the triangle collapses. If it's going to collapse, or then we can say it's not going to collapse. So this just defines the triangle set here. So we look at the triples here, and this is supposed to say for every stage they're not collinear or copunctal. So these are the initial points that will forever stay triangles. Okay? I think that's reasonably clear. So. Okay, so how hard is it to prove that such triangle sets exist, or such 0 sets exist? Okay. So let's just give this a more formal statement here. GDS sub t or sub z is the statement, okay, for every n, for all functions from n to the n to itself, this triangle set exists, right? Or correspondingly the 0 set exists here. So how hard is it to prove that these statements are true? So if it's formulated, we can think of this as something in second order number theory. Right? So it's a statement in analysis. And it turns out that these are equivalent to pi 1 comprehension, same theory as from last talk. So we can view this as saying that we need pi 1 comprehension to prove that there are sufficiently long ordinals that we can iterate this process along until we can view that the thing is eventually looping, right? The triangles are going around in a fixed pattern, or that they've collapsed at some point to 0. Right? So the setup that we have here, right, requires a substantial bit of second order number theory to prove that we have these sets. Right? So this is the sort of the game that I'm playing. Right? So how does one prove something like this? We use this infinite time register machines here, and I believe there was an attribution earlier on in one of the previous slides that this is joint work with Peter Köpke, the next 3 slides here. So what is an n register machine here? You just take a standard Shepardson-Sturgis register machine. It's got n registers. We think of the natural numbers R1 up to Rn at time alpha being given as over here. And what we're requiring at limit times in these machines is precisely the same funny limit process. We're having natural numbers in the machine. If the values at a limit stage creep off to infinity, we reset them back to 0. So the action of this machine looks just like points going around this torus. And we just use standard programs for these machines. We don't have to change any of that at all. We've just by fiat just set what's going to happen at limit stages. So we have to make up some sensible rule, and again, Miller, they just used, we've now just got a finite program, so they've said at limit stages they'll just say that the next instruction is the limit for the previous instruction numbers that have been used up to that point. And actually that rather nicely puts you at the head of the outermost loop of subroutines that were called cofinally in that ordinal. And it's just a nice effect of using this limit on the instruction numbers. Okay, now such a machine may halt at some time beta greater than or equal to omega. Right? It doesn't have to halt at a finite time anymore. Right? So the question is, how long does it take for a machine on a particular numerical input to halt? Right? So in essence, we solved the previous question by coding up onto register programs this function's action. And you can see, or you can imagine, if you've got a machine like this with n registers in, the contents of the registers, you can think of this as a point going around the torus. So we can think of the halting set for such a register machine here. Just trying to get some standard notation. We've got the ETH program on input on these n registers here, and one can ask questions about this HN set here. And amusingly, actually, what happens is for these register machines, once they're transfinite, actually the number of registers is important. And as the number of registers increases, the strength of the machine increases. So actually there's no universal ITRM, right? because of that fact. Right? On ordinary register machines, sufficiently small number of registers can compute for you a universal machine. But that doesn't happen for these ITRMs. So what this also implies is that the dimension counts for this kind of torus problem. Right? You increase the dimension, you're going to have to wait longer to see whether your triangle collapses. So again, just to formulate something a bit kind of second order number theoretically, let ITRM sub n be the assertion that the n register halting set exists. So we're asking for the set of integers here to exist, and it's going to need some second order number theory to prove there is such a set. The boldface ITRM is again saying for any particular oracle set Z here, and for any n, the n halting set, where you can imagine for yourselves this is the halting set here where I take an oracle Z that the program can consult en route. So what comes about is that you can show that there exists this set here, right? This n halting set here. This takes kp plus you need at least n admissible ordinals below you plus omega in order to prove that this set exists, right here. So in essence, this says how long an n-register machine will have to run on integers before you can tell whether it's ever going to hit 0, right, or whether it's going to halt. Right? You're going to have to go up to the n plus first admissible ordinal, and then you know that the machine is in an infinite loop. And so from pi11 CA0 you can prove ITRM. Conversely, well, this is just really just a restatement of what that converse would be. If you've got this is somehow the harder direction, if you want to show that on an ITRM with n registers, you can compute something like the nth hyperjump of 0. Right? You need some extra registers, right? You need n registers to store these values here. You need some extra registers as workspace, but there's a fixed k such that if you have n times k many registers, you can compute the nth hyperjump there. Okay, is there anyone want to ask anything? Okay, so this says perhaps what your straightforward guess might be as to how you would solve then this problem about whether these triangle sets or these zero sets exist. I mean, I've alluded to this already. If you've got a function from n to itself, you consider that coded up as some oracle z, and you just devise a program so that with input, the starting point here, and it's going to use some more registers, perhaps as I've mentioned. You just run the program and it'll just search for you to see whether the thing goes to the origin or not here. So this question then just becomes reducible to this question here. And as I've said, we need to go to this many plus 1 admissible ordinals, and then we'll know whether this is in this zero set or not. And if you believe what I've said there, then you can see how if we increase the dimension, we need more admissible ordinals. Okay, so let's play the game in other ways. Now let's think about rationals right here. Just take the rational unit interval and consider iterates of f. So you've got a kind of now rational torus, and think about the same kind of question. So this is something we can all do. Again, because it's rationals, we've got all of this action coded up by some oracle, if you like. But now the lim-inf operation is a little bit more problematic. Of course, the limit of these rationals after omega many stages, or limit number stages, may no longer be rational. Right? Okay, so we'll just say that there's no output in that case. The machine crashes. But now the lim-inf becomes a slightly more complicated statement. The lim-inf just on for these register machine registers, it's just a kind of sigma 2 or pi 2 statement. But now, if you think about what it is to calculate a rational lim-inf, you end up with something that's a pi 3 statement. You want to say something like, for all natural numbers, for all 1 on n's, there is an alpha such that for all later betas, you're kind of close within 1 on n of this limit. So it becomes a pi 3 statement, at least in the language of set theory. And indeed, so I tend to think of these things as just running along ordinals inside the constructible hierarchy. And if you've got an f on some starting n-tuple of rationals here, if it does stay rational all the time without crashing, if you go up to gamma, where gamma is the least pi 3 in f admissible ordinal, so it's pi3 reflecting in this admissible ordinal, then if the machine is continued to this stage, it'll stay continued. It'll stay running without crashing, and indeed you're in an infinite loop by this stage. So this is a large admissible ordinal, but I have no idea if that's best possible. Okay, the real thing, right, now. So we've got a function. Now on the real torus, let's say it's continuous function now, so this is more like what a real dynamical systems person would consider. They would consider infinitely many iterates, but just finite iterates of f, and typical thing they might ask is they would look at what is the limit set at stage omega. They would look at what subsequences they've got through all of the iterates and what limit points that they've got. So I'm suggesting here, let's just take the least of those possible limits. Again, this is just a limit in this situation. And we could take that limit as a starting point for the next round of iterations. Okay. Now, of course, we're not iterating just numbers or rationals. We've got reals to carry along. So basically, this means thinking about, say, the set of rationals that are below the current real value of our point. So we have to kind of carry infinite amounts of information along at each computational stage. There's no worry, of course, about crashing because we've fallen out of the rationals here. But again, it's still a pi3 kind of computation to work out what the limit is at these limit stages. So how long do we have to wait here? Right, so take f. Here I seem to have coded it up just as a member of bare space. Consider the following ordinal, zeta. We'll call it f extendable, well, 2 extendable because of a sigma 2 that occurs here, but I'll just say f extendable, is an ordinal such that in the L hierarchy over f, the zeta-th level of the L hierarchy of f, L zeta f, has got a proper sigma 2 end extension. So again, this is very high in the countable ordinal hierarchy, such as zeta is going to be a limit, is going to be a sigma 2 admissible, limit of sigma 2 admissibles. So we're talking large countable admissible ordinals. And I'm taking, let's take zeta f be the least such ordinal here. Then it turns out if you want to determine, say, the question whether the iterations of this f starting on some real x or other, suppose it goes through the origin at some point like this, then this can be determined by an iteration of this length here. Right? And you can perhaps see what's happening is if this is a pi3 calculation about f, one can see here that this pi3 statement here, this is going to go down from this, the calculation about the value at this stage will go down by sigma 2 elementarity to this L zeta f here at this stage. So you can suspect that the computations at this stage and this stage are going to be the same. Right? And this gives you some idea that at this stage you're kind of in a loop. What happens here is going to happen permanently afterwards for every additional sigma many stages here. So again, just to state this perhaps a little bit more formally, if you've got a statement, we just say let AQI be the statement for every function f, such an ordinal exists. We've got sufficiently many well orderings like this. Then you can prove the existence of these ordinals in pi1-3 comprehension, pi1-2 comprehension doesn't suffice here. Lower bounds. I'll just finish with this last slide. Is this the best possible way? Is this the best possible bound for such functions? Well, one avenue is to try and show that that's the best possible lower bound is to, you try and wire into this function f some codes for levels of the L hierarchy up to this ordinal zeta, something like this, or perhaps sigma 2 theories of these levels as you go on. The trouble is, you need to do this in some kind of continuous fashion, because we required that function was a continuous function. So one needs some kind of clever way of coding this kind of iterative process into such an f like this. An iterative process that will give you the L hierarchy into such a continuous function f. So that's the problem at the moment, and we need to do this in some continuous way. Okay, thank you.
So you have buried the ground set on which you compute. You start with omega, then you go to the rationals, and then you go to the
Yes.
okay. Have you considered changing the topology instead? So instead of computing on a torus, computing on a ball or so?
I suspect it doesn't make a lot of difference, but no, I haven't. I mean, I barely thought about this. I mean, this is sort of yes, I haven't really thought very much about it at all. But it was natural to think of these machines as being going around these integer toruses, but then, of course, dynamical systems are about the reals. And I was just trying to think of some way of extending these kind of iterates into the transfinite to see what kind of questions might come up. And that was just the first thing that occurred to me.
One question. Sorry, Sam. Go ahead. Sorry.
So a quick one. With normal register machines, it doesn't matter much what convention you adopt to stop.
Right.
Is the same true here, or is it a little bit more delicate?
No, I mean you just use the same program as you have. So if you address a function beyond the number number of instructions you've got, you can
That's
say
good
it's
enough. Okay.
it's good enough. Yeah.
In the first part, you spoke about n-tuples of integers, and you got a theorem saying that you need at least n admissible ordinals to show that nth level, for n you can prove termination. So this is sharp.
Yes.
You can prove that with less than n.
It won't work. Yes.
You have examples.
Yes. I mean, in terms of calculating. I mean, you can do it in various ways, but essentially you can just have the thing calculate the hyper jump for each stage, like that.
And each extra n, as you go
Yes.
from n to n plus 1, somehow you're requiring one extra inductive definition or something
Yes,
to come into play.
yes. I mean, you want to. I mean, of course, it's all in this funny limit style rule. I mean, the fact that when things go off to infinity, you reset to 0. So there's an inductive argument on the number of registers as to how, at limit stages, you look at a particular admissible ordinal and you look and see which registers have gone to 0 through the use of this limit rule. And you need to count down from the number of registers you've got through admissible ordinals to kind of guarantee that if this number of them are all 0, then you're in a proper genuine loop. So one does need each of those admissible ordinals to do that. That's a thumbnail sketch. Yes.
Did you look at the case where you have a different notion of limits? For example, so if you look at the coordinate and then you say you set it instead to some other coordinate, for example, to the next coordinate or something. I mean, maybe you could keep it going for longer this way, or I mean,
If you do a sort of shift in the registers?
Well, I mean, you basically when you define the limits of these functions, you instead of setting it to 0 like we do now,
Yes.
You set it, for example, to the next coordinate, the limit of the next coordinate, if that's defined, for example, or something like that.
I did
give a different result. I mean,
I didn't consider that.
not so nice, I agree, but it's.
Yeah, I didn't consider that. I think these mechanisms and these examples are sufficiently robust that small. I mean, I'm not saying this is small, but certainly small tweakings in it actually don't really make very much difference. I'm not sure whether this is one or not.
Is it possible to get some? You got some 3 or 4 ordinals occurring here. Is it possible to get more ordinals in between, or really ordinal notation systems out of this?
I don't know what a good ordinal notation system is.
Or it doesn't need to be a good one, maybe just any.
There's somebody to ask.
I mean, I think it's an art form, getting a good ordinal notation system, and it's not an art I'm good at or expert in. It's true that these ordinals are, I mean, you just have these first omega many admissible ordinals, and then there's this pi 3 reflecting ordinal, and then there's this huge jump till you get to these sigma 2 extendable ordinals. These, I guess, are just epiphenomena on these various kind of machine notions, or these various dynamical system notions, but no idea about other things in between. But I invite people to think about these questions.
Okay, so let's thank both speakers.
Thank you.
That was important.